Welcome to The Explainer. Today we are digging into the incredible science of survival. How do you build something that can actually withstand one of the most powerful forces on Earth, a massive explosion?
So let's just jump right in. When an explosion goes off, it unleashes this massive, almost instantaneous wave of pressure. How do you possibly build something to survive that? What does it really take to stop a shockwave dead in its tracks?
Okay, so your first thought might be just build a thicker, stronger wall, right? Pile on more concrete, more steel. But it turns out modern material science has found way more clever ways to handle a blast. It's really less about brute force and a whole lot more about smart design.
So before we can even think about designing a defense, we gotta understand what we're actually up against. What exactly is a blast, from a science point of view?
You see, the key thing here is that a blast isn't just a simple push. It's more like a 1-2 punch. First, you get this incredibly fast high-pressure shockwave that just slams into the surface, and that's immediately followed by the push from all the expanding gases from the explosion itself. The crazy part? This all happens in a tiny fraction of a second.
All right, so let's start with the basics, the classics. How do the traditional workhorses of construction, we're talking steel and concrete, how do they hold up against this kind of insane force?
Well, this is where you see the fundamental trade-off. Steel is super strong, and it's ductile, which means it can bend and absorb some of that energy. But a really powerful blast can still just tear it apart. Now, concrete is fantastic against compression, but it's brittle, so when it fails, it doesn't bend. It just shatters, sending all these dangerous chunks of debris flying everywhere.
So, if the classic materials just aren't enough on their own, how do we make them better? Well, the answer is to get them to work together, kind of like a team.
And this is a perfect way to see how composites work. Okay, so you start with your plain, brittle concrete. Then you mix in these tiny steel fibers. This creates this sort of web inside the concrete that holds it all together and lets it absorb way more energy. And finally, you spray on this rubbery coating of polyurea. This skin acts like a final shield. It absorbs that initial shock and it contains any fragments. You see? Each layer systematically covers the weakness of the one before it. It's pretty brilliant. And engineers have gotten really creative with this stuff. They combine steel and concrete into these incredibly powerful composite beams. Or for columns, they'll pack the reinforcing bars way tighter together to cut down on damage. They can even wrap a column in a thin steel jacket just to boost its strength. And get this one is kind of wild. Sometimes, adding holes to a steel plate can actually make it better at absorbing energy. It seems backward, but it allows the plate to deform in a much more controlled way.
But what if trying to block the force is the wrong idea entirely? Instead of building some unbreakable wall, what if you could just build something that soaks it all up?
This idea is a total game changer in blast protection. Absorbing the energy can be so much more effective than just trying to resist it with brute strength. The goal is to make that destructive force just disappear before it can do any real damage.
And the difference is absolutely staggering. Just look at how solid steel compares to materials like metallic foams and elastomers. These things are absolute superstars at dissipating energy. Their unique internal structures let them crush and stretch and deform, basically turning all that kinetic energy from the blast into heat. That energy never even gets to the thing you're trying to protect.
So how do these amazing materials actually pull this off? Well, metallic foams are filled with tiny little air pockets. When that shockwave hits, these pockets just collapse, and in doing so, they absorb a massive amount of energy. Elastomers, like rubber, stretch and deform all the way down at a molecular level. But it's not just the material itself. The shape is also key. For example, if you form rubber into little pyramids, you can actually tune it to absorb energy even more efficiently.
Okay, now let's really jump ahead to the cutting edge. This whole quest for resilience is evolving all the way down to the microscopic level.
Now, these names might sound like something straight out of science fiction, but this is the next generation of protection. We're talking about composites reinforced with microscopic materials like graphene or carbon nanotubes, or even honeycombs with ascetic properties, which is a wild concept where the material actually gets thicker when you stretch it. Seriously, we are talking about materials that are being engineered literally atom by atom.
And that brings us to a truly revolutionary idea. Imagine a single piece of material with no layers at all, but instead it smoothly transitions from being super hard and rigid on the outside to being soft and absorbent on the inside. That's a functionally graded material. It can meet a blast with a hard face and then just seamlessly dissipate the energy as it travels through. It's really the best of both worlds in one elegant solution.
So, after looking at everything from classic materials to advanced composites to these futuristic smart materials, what's the big takeaway here? What's the ultimate lesson?
Well, the first thing we've definitely learned is that there's no single magic bullet. There is no one perfect material that can solve this incredibly complex problem. The real quest isn't for some miracle substance. No, instead, the whole philosophy now is about creating an intelligent system. It's a total shift away from brute force thinking. The goal is to have multiple layers, and each layer has a very specific job to do. One layer deflects the impact, the next one absorbs the energy, and a final one contains any damage that might be left.
And that leaves us with a pretty fascinating thought. These same principles of smart, layered, functionally graded systems, they could be used to build for just about any extreme environment you can think of, from the crushing pressure of the deep sea to the vacuum of space. The science of surviving a blast is ultimately teaching us how to survive, well, anything, which really makes you wonder, what will we engineer for next?